Okay, we're on Unit 2 now, and our first set of notes is the definition of derivative. Okay, so your objectives are to be able to identify the derivative of a function as a limit of a difference quotient, which you've actually done already. Use correct notation for derivatives, and then even for the next set of notes, use power product and quotient rules for derivatives, okay? So the definition first, the derivative of a function is defined as the limit of a difference quotient. It can be determined using a variety of strategies, including the instantaneous rate of change, which you've already found in the last chapter, okay? So, a derivative in algebra is really just the slope, which is the average rate of change. Usually you are only given a line to find that of in algebra, okay? So if you look at a line here, you could have, if you had coordinate points, you could use the slope formula. If you're given a function, this comes from using a function on an interval. And this is what we did last unit. Your slope is f of b minus f of a all over b minus a. Okay, but a lot of times, especially when we don't have a line, we're going to be changing the formula to x and x plus h, then be taking a limit. Okay, so your interval is going to be x comma x plus h instead of from a to b. Okay, and like I said, we've already kind of talked about that with instantaneous rate of change, so that shouldn't be anything new. Okay? But especially with curves and other kinds of functions, we want to know the slope of the curve. Okay, and so we don't have just a slope formula where you can pick points and find their slope, okay? So like if you were doing that in Algebra 1 and you were just picking two random coordinate points and finding their slope, you'd be finding the rate of change along a line like this, okay? Is that really the most accurate way to measure this change of the curve? I mean, it's not, because between here and here, look how far off your real curve is going, okay? That's why we have to use a derivative. And so when you're taking the limit, you're really looking at it getting closer and closer and closer to 0, and then eventually we'll learn how to find the rate of the tangent line, which is the best approximation to the curve, okay? So this is a tangent line. It's hitting the curve once, okay? And then your other lines are secant to the curve. They're hitting twice, okay? So a tangent curve is the most accurate way to find your rate of change at a point, okay? So, like I just said, the best approximation of a curve is to find the slope of the tangent line to the curve. Because all of those secant lines, you could see, didn't really follow that curve very well. Okay, so to approximate, we use the limit of the slope of the tangent line as h approaches 0, which is also the same thing as taking the instantaneous rate of change. So when you're doing that, you were finding a derivative of a function, okay? And so now, this limit here, which is your instantaneous rate of change at a point, that's f prime of x, which is, that's a derivative, okay? So the derivative of a function is the slope of the tangent line at any point on the curve. And there's a lot of different ways to write derivatives. So I kind of want you to know whenever you see a certain notation, it's all asking the same thing, okay? So, notation, y prime is a way to ask the derivative of y if you're given a y equals, okay? Next, this is probably what you'll see the most, f prime of x. So how do we say that? F prime of x. That means the derivative of f with respect to x. But really, guys, these are asking the same thing. Okay, it's just a derivative of, depending on what you're given, something a little different, but you're still going to do the same process, okay? Next, you may see dy dx, especially when we're doing integration next chapter. So literally you just say dy dx. Okay, and that is the derivative of y with respect to x. And if you don't see y, maybe you'll see an f, then you'll have df dx. So df dx is how you say that. Derivative of f with respect to x, and then you still might see this, but probably will see this the least amount, but d over dx of f of x. Okay, and that literally means take the derivative of f of x. Okay, this means take the derivative of f of x. So what do we really say here, though? dx of f of x. Just so you know how to read it. Okay, derivative of f at x is what would come out of there. Okay? All right, so let's go to the back and start finding some derivatives. Okay, now, if you notice, this is going to be the same kind of process of the instantaneous rate of change, but we don't, for the first few, have an x value, okay? So we're still going to take the limit as h approaches 0 of f of x plus h minus f of x all over h, okay, but not at a certain x value. So you're going to leave it with x's in your answer, okay? Which some of you practice, some of you liked plugging in for x, but for these, we have to leave x in our answer, okay? So the derivative f prime of x of the square root of x plus 1, we're going to find that by taking the instantaneous rate of change formula, using that, and not plugging in a certain x value, okay? So f of x plus h minus f of x all over h. All right, let's do that. So this would equal limit as h approaches 0 of the square root of x plus h plus 1 minus square root of x plus 1 all over h. Okay, so I just plugged in x plus h into the function, and then I did minus the original function all over h. And of course, we're going to have to multiply by the conjugate here. All right, so times the square root of x plus h plus 1 plus square root of x plus 1 all over square root of x plus h plus 1 plus the square root of x plus 1. Okay? So that's going to give me the limit as h approaches 0 of, when you FOIL up top there, remember, don't break your denominator up. Write it exactly how you see it. But when you FOIL the top, you're going to get x plus h plus 1 minus x minus 1. Okay, because this would be minus x plus 1, and so I distributed here. All over h times square root of x plus h plus 1 plus square root of x plus 1. There we go. Okay, so now things should start canceling. And then my h's are going to cancel, and I'm going to get 1 on the numerator. All right, so now I'm at limit as h approaches 0 of 1 over square root of x plus h plus 1 plus square root of x plus 1. All right, and then we're going to plug in 0 for h. So once we've taken that limit, we're plugging in 0 for h. Okay, so this is 1 over square root of x plus 1 plus square root of x plus 1, which is 1 over 2 square roots of x plus 1. That's the derivative. Okay, that's f prime of x. All right, derivative there. All right, so I took up like that entire page. Let me go ahead and do the derivative of 1 over x right here, and then I'll probably have to pause the video or stop the video and grab another sheet for the rest. Okay, so y prime of x, which is really asking the same thing, or y prime of 1 over x, we're going to do the same thing there. Okay, so limit as h approaches 0 of f of x plus h would be 1 over x plus h minus 1 over x all over h. Okay, so f of x plus h minus f of x all over h. Okay, and so now this is the common denominator type of problem. So your common denominator of the numerator is going to be x times x plus h. Okay, your first group is missing an x, so I need to times that by x over x. So that will give me x for my first term, right? And then the minus, let's just copy the minus for now. Okay, so the second group is missing x plus h. Yeah, x plus h. Okay, so x minus x plus h. Okay, this is your whole common denominator. And then I'm going to write that again, but then I'm going to times it by 1 over h from here. So I don't have a fraction over a fraction. So limit as h approaches 0 of, x minus h all over x times x plus h times 1 over h. Okay, that's where we're at here. And now hopefully you can see why it's very important that we understood how to take a limit before we moved on. Okay, so these cancel, and I'm at, well, the h's will cancel too, right? And so I'm at limit as h approaches 0 of, that's a negative 1 all over x times x plus h. There we go. Now we can take the limit because we won't be dividing by 0. So this is negative 1 over x times x, negative 1 over x squared. That is your y prime of x, y prime. That's your second derivative. Okay, we'll try a couple more, but I'm going to have to get another sheet of paper, so we'll have a second video.